Hello, welcome to the recitation week 9 for EE2423 network theory. Today I will be introducing and discussing some properties of complex number. So, complex number. So I believe that you already known what is complex number, but here I will be reviewing it for the purpose of network analysis. Okay, so first, what is complex number? Consider a quadratic equation. So we have quadratic equation x squared plus 1 equals 0. So this is a quadratic equation, and what is the roots? So what are the roots of this quadratic equation? Let's see. So x squared must be equals to minus 1, so x should be plus minus square root of minus 1, right? But we know that the square root of minus 1 does not exist in a real number or the set of real number, right? So previously, when we were in junior high school, we were told that okay, when we have square root of minus 1, there is no root for this quadratic equation. But we know that that's not true, right? So mathematicians have developed the concept of imaginary number. So if we define j, or sometimes it is also referred to I as square root of minus 1, then we can express the roots for example, this quadratic equation. So we know that x squared plus 1 equals 0 is, and the roots of this quadratic equation are plus minus square root of minus 1, which is plus minus j or plus minus I, right? So some people use j, other use I to represent complex number, particularly square root of minus 1. But in network theory, usually we refer currents as I, right? So that's why here mostly we will refer square root of minus 1 as j. Okay, so let's remember that we define j. So this is a definition. J is square root of minus 1. Okay, this way if we have another polynomial quadratic equation, and we can write the roots as x squared is must be equal to minus 16, so x must be plus minus square root of minus 16, which is plus minus square root of 16 multiplied by minus 1, right? So plus minus square root of 16 is 4, square root of minus 1, so plus minus 4j. Okay, so this is, I can say that this is section 1 definition of complex number. Next, we will discuss about power of j. Okay, so we define j as square root of minus 1. Hence j squared is square root of minus 1 multiplied by itself, so we have square root of minus 1 squared, which is minus 1. Okay, how about j cube? Well, j cube is j squared times j, right? But we know j squared is minus 1, so it is just minus j. What about j to the 4? J to the 4 is j squared, right? So minus 1 squared, which is 1. What about j5? j5 is j4 times j, so 1 times j, it is just j. So any n power of j can be represented by either j squared, j cube, or j4. Okay, for example, what is j to the power of 2307? Well, you can use modulus of 4, right? Use the modulus of 4, so you can write this as j to the power of 2304, because 2304 is divisible by 4, and the remainder is 7 minus 4 is 3. Okay, that this is the something to the power of 4, which is actually 576 multiplied by j cube. So we know that this is 1, and j cube is minus j, so this is just minus j. Okay, next I will describing the general form of complex number. In general form of complex number, so here is the general form of complex number. Okay, before that, for example, suppose that I have this quadratic equation, x squared plus 2x plus 10 equals 0. And what are the roots? Okay, we know that the roots are minus b plus minus square root of b square minus 4ac over 2a, where the a here is 1, b is 2, and c is 10, so minus 2 over 2 plus minus square root of 2 squared is 4, minus 4, minus 4, so minus 20. It's 40, because 4 times 10, so minus 2 over 2 plus minus square root of minus 36. Okay, so you can write this as minus 1 plus minus square root of minus 36 over 4. This is equivalent to minus 1 plus minus 6 over 2j, which is minus 1 plus minus 3j. Okay, so in general, complex numbers can be represented by real part. So we have real part and imaginary part. So say z is a complex number, and And the set of complex number usually is referred to as C complex. Then Z can be written as A plus B times J, where A and B are real numbers. Okay, so this is a general form of complex number. So if you have a complex number Z, then it can be decomposed into real part and imaginary part. So A is defined as a real, so the real part of Z, and B is the imaginary part of Z. Okay, and there are also special cases. So for example, if I have, say, -4, so -4, so it means that it says we can see -4 as a complex number where it doesn't have imaginary part, or the imaginary part is 0. Similarly, where I have, for example, 16J, then we can say that this is a real number where the real part is 0 and it only contains imaginary part. Okay, so rules of algebra. So this is number 4. Okay, so suppose that I have two complex numbers, a1 plus b1 j, and z2 is a2 plus b2 j. Then what is the sum? So sum z1 plus z2 is nothing but we sum the real part, a1 plus b1 j plus a2 plus b2 j, just simply a1 plus a2 plus b1 plus b2 j. Okay, and the difference is similar. So if we subtract z1 with z2, then a1 plus b1 j minus a2 plus b2 j, so we must have a1 minus a2 plus b1 minus b2 j. Okay, so that's the first rule for addition and subtraction. Next, how about multiplication or product? So what if z1 is multiplied by z2? Well, we can work this out. So a1 plus b1 j multiplied by a2 plus b2 j, then a1 a2 plus a2 b1 j plus a1 b2 j plus b1 b2 j squared. You know that j squared is -1, so a1 a2 minus b1 b2 plus a1 b2 plus a2 b1 j. All right, so that's the product. Now the third one is about quotient, or well, what is z1 divided by z2, for example. To find out what is the expression for z1 divided by z2, we need to discuss about complex conjugate first. So what is complex conjugate. So say I have a complex number, right? Then a z bar, which is complex conjugate. So z bar is complex conjugate say that z is a plus bj, then z bar is a minus bj. That's it. So we just need to change the sign of the imaginary part. Okay, so if you have a complex number and you want to find what is the corresponding complex conjugate, then you just need to change the sign for the imaginary part. Okay, so we can say that a minus bj is a complex conjugate of a plus bj, or a plus bj is a complex conjugate of a minus bj. Okay, so from this we obtain two properties. So what is a z plus z bar? Then we have a plus bj plus a minus bj. Then here we can recover the real part of z, right? So a is 1/2 z plus z bar, which is the real part. Okay, right? And if z is subtracted with z bar, then a plus bj minus a minus bj, then you know that this is 2bj. So b is 1, so bj is 1/2 z plus z bar, right? Or v, which is the imaginary part. So 1/2 z plus z bar is the imaginary part of z. Alright, and if we multiply z with its conjugate, then what do we have? We will have a plus bj multiplied by a minus bj, and we will get a square minus b squared times j squared. So this is actually a squared plus b squared. Okay, so if you multiply z with its conjugate, then we will get a squared plus b squared. Now we can derive the expression for quotient. So what if z1 is divided by z2? Then assuming that z2 is not 0, then z1 over z2, you can multiply this with the conjugate of z2. So z2 conjugate over z2 conjugate, right? So we will have a plus bj. I haven't defined what is z1. So we use the same z1. So z1 is a1 plus b1j, and z2 is a2 plus b2j. So z1 is a1 plus b1j, and z2 is a2 plus b2j, and the conjugate is just minus b2j. The same with this, a2 minus b2j. So you can work this out and you will get a1 a2 plus b1 b2 over a2 squared plus b2 squared plus a2 b1 minus a1 b2. So over a2 squared plus b2 squared j. Okay, so this is the expression for coefficient. So the trick here is, say if you need to compute, say z1 z2 and they are complex number, then if you want to compute z1 over z2, then you multiply with the complex conjugate of the denominator, right? z2 bar and z2 bar, because this is nothing but 1, right? So this is the trick if you want to compute the complex conjugate. And we say that z1 must be equal to z2 if and only if, right, a1 equals a2 and b1 equals b2. Very simple. Or the real part of z1 is equal to real part of z2 and also the imaginary part. So if the imaginary part and the real part, they are equal, then we have z1 equals z2. And we can say that what is 0 in complex number. So z1 is 0 if a is 0, sorry, only z. So z is 0 if a is 0 and b is 0. Okay, for example, I have z1 is 3 plus alpha j and z2 is beta minus 5j. Then question is, what are the values of alpha and beta such that z1, so find alpha and beta such that z1 plus z2 is 0. So let's see. So z1 plus z2 is 3 plus beta plus alpha minus 5j, right? So if you want this addition to be 0, then beta must be minus 3 and alpha should be 5. Okay, so these are the rules. We also have properties. So number 5, properties of complex number. We have commutative. So commutativity, so say z1 z2 are two complex numbers, then the addition and the product, they are commutative, so they are commute. For example, z1, so this is z2, so z1 plus z2 is equivalent to z2 plus z1. Same with the product, so z1 multiplied by z2 is equal to z2 multiplied by z1. So they commute with addition and multiplication. Next is associative. The same if z1 z2 are complex numbers. Actually we have 3 for this property, z3. Then if we sum the first two first and then add it with the third one, then we will get the same result as adding the first one with the sum of the last two. The same with multiplication, so z1 multiplied by z2 and then we multiply it by z3, we will get the same result as z1 multiplied by the product of z2 multiplied by z3. So we have also associativity for the addition and multiplication. The third one is distributive. Again, z1 z2 z3, they are complex numbers, so we see z1 multiplied by z2 plus z3, we will get z1 z2 plus z1 z3. Okay, next number 6, geometric representation. So there is a way to illustrate complex numbers. So we have a y and x-axis. Say the x-axis is usually the real part, right, and the y-axis or the vertical one is the imaginary part. This way, say if we have z is a complex number a plus bj, so we will say this is a and this is b, so the complex number is at this point right here, c. So z is imaginary part or j, so the imaginary part represents the symbol j or square root of -1, so z is nothing but a plus, so this is bj, sorry, yeah, a plus bj. So this factor here represents this complex number z. Okay, so again a is the real part and b is the imaginary part, and this allows us to represent complex number in a different way. So usually this representation is referred to as rectangular representation, but since we have a factor, now we can define the length of z. So this is the length of z, so this is the length of this factor, which is by using trigonometry, then we know that the length of this line is nothing but a squared plus b squared, and by defining this angle as theta, so theta, so we know that the tangent of theta is b over a. Okay, so we can represent complex number with the modulus. So this is modulus. This is called angular representation or polar representation. Okay, sorry, this will be square root, right? All right. So if we draw these lines, then we know that what is cos theta. So cos theta is a over the modulus, right? And sin theta is b over the modulus, right? So this way we can write z as the modulus times cos theta plus the modulus z times sin theta multiplied by j. Why? Because we have defined this, right? So because cos theta is a over the modulus and sin theta is b over the modulus, since they cancel, then we will get our number a plus bj. Okay, so this is nothing but the modulus multiplied by cos theta plus sin theta times j. Theta is referred to as the argument or the angle, and here is the modulus. Okay, or we say that theta is the argument of z. So this in general how we can represent a complex number either in rectangular form or in polar form. Okay, so that's the end of this lecture. So if you have any question, please come to my office hour, or you can send me email. All right, thank you for your attention, and I'll see you next time.